This video is an introduction to galvanic cells, chapter 18. So one of the things we learned about was a redox reaction. The other key piece we need to learn about with electrochemistry is basically changing chemical energy into electrical energy or electrical current. The thing we focus on in chapter 18 is what are called galvanic cells. When it says galvanic or voltaic, it means it's spontaneous. And what do we know from thermodynamics when we studied it? Spontaneous means it happens without adding any energy to it. So it's a chemical reaction which will generate an electrical current. An electrolytic cell is a non-spontaneous reaction. That would be like your cell phone battery that you have to charge all the time. It doesn't just automatically generate current, but it needs to be charged. So that's a key difference. So we're really going to focus on galvanic cells mostly. All right. We learned before that oxidation, a couple things you need to know, is a loss of electrons. And basically what happens is the oxidation number goes up. So like for example, if you look here, the oxidation number of magnesium is 0 because it's an element. Here, the oxidation number of magnesium is 2+. So we would count that as an oxidation. A reduction is a gain of electrons. What that means is your oxidation number is going to go down. So like here, magnesium has a oxidation number of 2+. Here it's 0. That would be considered that is a reduction. Now, we talked about a galvanic cell. We have two things happening in a galvanic cell. You have an oxidation and a reduction. So if we look here, the first thing we can do is assign oxidation numbers. Zinc has an oxidation number of 0 because it's an element. Copper is 2+ because it's an ion. Zinc is 2+ because it's the charge of the ion, and copper is 0. So what's happening is zinc is going from 0 to 2+. That would represent an oxidation. Copper is going from 2+ to 0. That represents a reduction. So when we talk about a galvanic cell, it's a redox reaction. A reduction and an oxidation combined together. Now, in a galvanic cell, it happens in two compartments. It has two parts to it. It has an anode and it has a cathode. And then you get an overall reaction. What is going to be your best friend is, well, first thing you have to understand is when we talk about a cathode, so this represents, is an easy way to remember it. A cathode, think of the word car, think of the two words car audio. Think cathode, reduction, easy way to remember it, and anode, oxidation. So you're going to hear me say car audio a lot in class when we're referring to these. The C represents cathode, it goes cathode reduction, anode oxidation. That's what I mean. It's a simple way to remember it. Your best friend is going to be a reduction table in this unit. So if we look right here, this is a standard reduction table. This is the exact same one you provided on the AP exam. If you notice, the electrical potential or the voltage is listed on the far right-hand side. These are all reductions because it's a reduction table. Notice the electrons are always on the left-hand side because there's a reduction going on. This is going from 0 to -1, which is a reduction. Fluorine is the best reducer, and it produces 2.87 volts when it happens. As you go down the list, you notice the voltage drops and gets lower and lower and lower, and then finally becomes negative. This is the best tool to figure out a galvanic cell. There's a simple process to doing it I'm going to show you. Here's the way it works. If you have like this is a picture of a galvanic cell. You have a galvanic cell that either involves copper, if you look right here, copper 2+, 2 electrons, and zinc to zinc 2+ with 2 electrons. If I go back to the scale, I see copper 2+ with 2 electrons. I see it right there. If I look further down on my reduction table, I see zinc all the way down here on the bottom. They're both listed as reductions. The way it works when you look at a reduction table is this. If you need to make a galvanic cell, the higher one is always the cathode reduction, car. The bottom one is the anode oxidation. So this would be, if you're building a galvanic cell, at your cathode, you would have a reduction reaction, which is always going to be the higher one on the table. The anode would always be the one that's lower on the table. So what I would have to do is I automatically flip this reaction. When I flip this reaction, Zn2+ plus 2 electrons equals Zn as a solid. I change the sign. This goes from being negative 0.76 to positive 0.76. So ultimately, when I go to get my galvanic cell and I put this together, I take Cu2+, plus 2 electrons. Let me go back to this. It goes Cu2 plus 2 electrons. Copper is a solid. I keep it the same because it's higher. It's on the top of the reduction table. This is on the bottom of the reduction table, which means I flip it. So when I flip it, I basically flip the reaction over. So Zn arrow Zn2 plus 2 electrons. Since the electron's on the right-hand side, it's an oxidation. Now if I go back and look at the values on the table, copper is 0.34, so I keep it the same. So if I come over here, I would write right here, the copper is going to have a voltage of, or E cell potential, we'll say E cell, of 0.34. Then I go back and I look at my zinc. If I look at zinc on the table, zinc has a value of negative 0.76, but since we flipped it, since it's an oxidation, it's going to become positive. So ultimately I put positive 0.76 here. And then what I do is if I add the oxidation and the reduction, if I add them together, I get what's called the overall cell potential. So what I get is when I add 0.76 and 0.34 together, I get 0.110 volts. That is called my E naught, or my cell potential. E cell value is what we call it in AP chemistry. So that's my E cell potential. If E cell is positive, we know the reaction is spontaneous. But a galvanic cell is always spontaneous, so that's why if you take the value on the top of the table, flip the value on the bottom, you'll always get a positive number. To get the overall cell reaction, I cancel the electrons. The electrons cancel, I don't need to multiply, so in the end, this is my overall reaction down here. Now, when I go to diagram out an electrochemical cell, what I notice is this. I put the oxidation reaction on the bottom here. If I notice, whatever the solid is the electrode. So the electrode is made of copper. Here I have zinc solid. This is actually my reduction because the electron's on the right hand side or left hand side. If you look here, I have zinc as a solid going to Zn2 plus with 2 electrons. This electrode is made out of zinc. So I'm going to draw this as out of zinc, and then I have the other ion, Zn2 plus. This is Cu2 plus right here. So ultimately what's happening is this is losing electrons, which are going to travel up the wire, go through this way, light up the bulb, and go back down this way. That's what an electrochemical cell is. It's basically forcing the electrons to go from one compartment to another, either powering something or lighting up a light bulb or something like that. The purpose of the salt bridge is to complete the electric circuit, because without it you would have a buildup of a positive or negative charge. So ultimately what happens is we use something like KCl or KNO3 or something like that that has positive ions that will go one direction, negative ions that will go the other direction to balance out charge. Now, the other thing we label is what's called the cathode and the anode. We know from car audio, since this is a reduction, car audio, if you look right here, cathode reduction, that's basically going to be associated with my reduction reaction. There's a couple things. The sign for it you have to be aware of, the fact that electrons flow to it. I'm going to show you a summary in a second. And the anode is where oxidation occurs, and we'll talk about what that is. So if you look, these are some key things. If you're talking about an anode, what do you know? You know automatically from car audio it's where oxidation occurs. It's also the place where electrons are produced, and then anions migrate towards it. So any basically negative ion will migrate towards it to prevent the buildup of a positive charge. And overall, in an electrochemical cell, it's associated with a negative sign. So if you're talking about an anode on a cell diagram, you would give it a negative sign. Basically, everything's the opposite for a cathode. A cathode has a positive sign associated with it. It's where reduction occurs, because remember car audio. So there's car, CR, cathode reduction, anode oxidation. It's where electrons are consumed, and ultimately cations will migrate towards an electrochemical cell. So how do you put all this information together to produce an electrochemical cell? Here's an example. I have Mn2 plus 2 electrons, Mn is a solid, Cr3 plus 3 electrons, chromium is a solid. If you look, they want me to make a voltaic cell. Well, the first thing I'm going to do is find my best friend, which is going to be my reduction table. So if I come over here and I look at my reduction table, I have to find both of those. So if I go back and look, I'm looking for Mn2 plus and Cr3 plus. Be careful, it's got to match exactly. So if I look right here, notice this one right here was Cr3 3 plus plus 1 electron. That's not what I'm looking for. I can't use that one. But I find when I'm looking at the table, I see Cr3 plus plus 3 electrons equals Cr as a solid. There's 1. And I also find Mn2 plus plus 2 electrons is equal to Mn as a solid. So I found my two items that I want to make a galvanic cell or voltaic cell with. I'm going to write CrAO. What does this mean? This is going to be my cathode and my reduction. I keep it the same. So if I go back over here, I'm going to keep this the same. And it was, I believe it was 0.74. Oh, it's negative 0.74. So it's negative 0.74 right there. So I'm going to go back here and I'm going to write, see here, negative 0.74, which means I have to flip this reaction. Since this is my cathode reduction, I'm going to flip this sucker. I'm going to write Mn as a solid. Arrow, I'm going to get Mn2 plus plus 2 electrons. And then I'm going to go back and grab the value, which I forgot. Mn is negative 1.18 as a reduction. When I flip it over, I get an oxidation. I get 1.18 positive. So I get a positive 1.18. So the first thing that I'm going to need to do is cancel the electrons. Right now, the electrons don't cancel. So what I need to do is find the lowest common multiplier like I do with a redox reaction. So basically I have 3 electrons on this side, 2 electrons on this side. So I'm going to multiply this whole thing by 2, multiply this whole thing by 3. This is going to be 2, this is going to be 6, this is going to be 2, and I don't ever multiply through. It's not like in the previous calculations we've done with reactions, the number doesn't carry out to the E cell value at the end. So I'm going to leave that alone as negative 0.74. The next thing I'm going to do is multiply this by 3, so this would be 3, 3, 6, and I leave the positive 1.18. So the next thing I need to do is do the math and add the two together. So I'm going to take 1.18 and then I'm going to add it to a negative 0.74, and ultimately I am going to get a 0.44, positive 0.44 E cell value. What does that tell me? That tells me that the reaction is spontaneous. It's a spontaneous reaction when E cell is positive, but I already knew that because when I grabbed them off the reduction table, I basically made the cathode out of the higher one, the anode out of the bottom one, and flipped it. So ultimately I have that. Now let's say I wanted to draw an electrochemical cell with this. So if I asked you to draw an electrochemical cell, what would I have you do? Well, if you look, I would basically do this. I would go here. Let's see if I can do it. Go down here, I'm going to extend the page. So it would look like this when I go to draw it. I would basically draw one cell and another cell, and I would write the reactions underneath. So I'm going to just pick, I'll write Mn as a solid here, arrow Mn2 plus 2 electrons. And then I'm going to write, actually it's 3, 3, and 3 in the balanced equation. And then what I'm going to do is I'm going to come up here and I'm going to grab 2 Cr3 plus, what was it, 3 electrons. So it's 6 electrons actually. Actually, I could just write the half reaction. Cr is a solid. And then what I'm going to do is I'm going to draw the electrodes. The electrode's going to be made of Cr. The electrons are always the solid. Cr is a solid. This is going to be Mn as a solid, like this. I'll draw a little random salt bridge in there, and then I have a wire that connects the two electrodes to each other. Now, electrons always flow from the anode to the cathode. So we said this was the anode, the Mn. So basically, this would be labeled, if this is the anode, this would be associated with a negative sign, this would be associated with a positive sign, and the electrons would flow this direction. So the flow of the electrons that direction, and if this is a voltmeter, let's say, the voltmeter would read 0.44. The other thing I do is I add the ion. Whenever the ions are just written in the beaker, so I'd write Mn2 plus, and I'd write Cr3 plus. And that's how you basically draw an electrochemical cell, if you had to draw it out and try it. You basically make whatever the solid is in each reaction, you make the electrode, write the ion inside the beaker, just draw a salt bridge, and then the E cell value that you calculated out, you put there up in the top. And that's how you do it. But ultimately, the thing that you really want to understand is this. If you have a reduction table, like you have a reduction table right here, if you have a reduction table, it makes it very easy to figure out a voltaic cell. Just remember, whoever's higher up on there is going to be, if it's voltaic, is going to be your cathode, and that's going to be a reduction. Whoever's lower is going to be your anode and your oxidation. You flip it, change the sign, add the two values together, and you get your E naught or E cell value, which basically will tell you whether or not the reaction is spontaneous or non-spontaneous. If it's positive, it will be spontaneous.